Good morning, everyone. Thank you for joining us today.
Great to be back.
We're back for another deep dive, and if you tuned into our last session, you know we explored the foundational concepts and diverse applications of the Internet of Things.
Yeah, we covered a lot of ground on what IoT is and where you find it.
Exactly. So today we're building directly on that, peeling back the layers to reveal the absolute backbone of any robust IoT system. We're diving deep into Internet of Things, architecture, and design principles.
And this is so crucial. Think of it this way. If an IoT system is a sprawling digital metropolis, its architecture isn't just a blueprint. It's the very DNA.
The DNA, I like that.
Yeah, it dictates how every road, every building, every utility line is laid out. Without this meticulously crafted plan, you don't get a functional, secure, and sustainable city. Instead, you get chaos, security vulnerabilities, and a system that simply cannot adapt or scale.
Which is useless in the real world.
Pretty much. And this deep dive is particularly vital for anyone grappling with the complexities of industrial IoT, especially in critical sectors like advanced manufacturing, logistics, energy management, places where reliability and efficiency are absolutely non-negotiable.
Right. It's about understanding the intricate dance, really, of how billions of devices connect, how raw data is not just transported but transformed into actionable intelligence, and how that ultimately delivers tangible value to us, the end users, or to the business.
Exactly. The whole value chain.
So to really unpack this complex topic, we've structured our deep dive as a comprehensive Q&A session. We'll walk you through the core questions that underpin this entire field, ensuring you grasp the essential principles.
And to give you a clear roadmap for our discussion today, we thought it best to just lay out all the questions we'll be tackling first. We'll address these sequentially, building up the architectural picture piece by piece.
Makes sense.
So here's what we'll cover. First, what is the most straightforward and widely referenced model for understanding IoT architecture? Second, can you briefly describe each of those three layers? Third, the document notes that the three-layer model can be an oversimplification. Why was a more detailed five-layer model developed? Fourth, what are the functions of these two new layers, the middleware and business layers? Fifth, when it comes to actually designing an IoT system, what is the top-down approach? Sixth, what about the opposite method, the bottom-up approach? Seventh, which approach is more common in practice? Eighth, bringing an IoT product to market is a complex journey. Can you outline the main stages of the IoT development lifecycle? Ninth, during the development phase, what are the different parallel tracks of work that need to happen? 10th, testing an IoT system seems particularly complex. What are some of the different facets of testing required? 11th, what is considered the single greatest challenge in IoT design? 12th, besides security, what is another significant barrier to creating truly integrated IoT systems? 13th, for many battery-powered IoT devices deployed in remote locations, what is a critical design constraint? And finally, 14th, to conclude, what is the key takeaway regarding the importance of architecture in any successful IoT system?
Okay, that's quite a list. That's our blueprint for today's deep dive. So let's start right at the beginning with the foundational understanding. Question number 1. What is the most straightforward and widely referenced model for understanding IoT architecture?
Right. The go-to model, the one that really helps simplify the immense complexity into digestible parts, is the three-layer architecture.
Okay, the three-layer model.
Yeah. Give you that high-level foundational overview. It basically distills the entire system down into three distinct logical layers, and each layer has a very specific core function.
Why is it so widely used?
Well, it's crucial for getting your head around the basic information flow, how stuff goes from the raw physical world, sensors and things, all the way up to the digital application that actually provides some value. It's simple, it's pretty intuitive, and it's a really great starting point for anyone just entering this space.
Okay, so that's our basic conceptual framework. Let's dive into that then. Question 2. Can you walk us through each of those three layers? What's actually happening at each stage?
Absolutely. So the first layer, the bottom layer, and arguably the most tangible one is the perception layer.
Perception, like sensing things.
Exactly. Think of this as the senses and, interestingly, the muscles of the IoT system.
Yeah.
It's the point where the digital world directly interfaces with the physical environment around us.
Okay.
At its core, this layer is populated by sensors. These are the IoT sensory organs. And they're just tirelessly collecting information about the world.
And we're not just talking temperature sensors here.
Oh, definitely not. It's everything from, say, vibration sensors detecting tiny anomalies in factory machinery that might predict a failure, to optical sensors checking product quality on an assembly line, or even advanced chemical sensors monitoring the composition inside industrial vats. Their job is basically to convert real-world physical parameters, like temperature, motion, light, humidity, pressure, whatever it is, into digital signals that the rest of the system can understand.
How do they do that conversion?
Often, it involves things like analog to digital converters or ADCs. They take that continuous, messy, analog physical data and turn it into discrete digital values, ones and zeros, basically.
Okay, so translating the analog world into digital, you also mentioned muscles.
Right, the
Yep.
muscles, those are the actuators. So if sensors perceive, actuators act. These are the devices that perform physical actions out in the world based on commands they receive from the higher layers of the system.
Like what sort of actions?
Well, an actuator might adjust a valve to regulate water flow, or turn off a motor if a sensor detects a dangerous overheating situation, or maybe lock a door in a smart building system.
Got it. So sensors read, actuators do.
Precisely. The perception layer is this critical bridge, both sensing the state of the physical world and making changes within it. And the real challenge here isn't just having sensors and actuators.
Yeah.
It's ensuring their accuracy, their reliability over time, managing things like sensor calibration drift, especially when they're stuck out in harsh industrial environments for years.
Yeah.
That's tough.
Fascinating. So, okay, once that raw data is captured by the sensors, how does it actually move through the system? What's the next layer responsible for that part?
That's where the network layer comes in. You'll often hear it called the connectivity layer as well.
Right, connectivity. Makes sense.
This is the communication backbone. It's kind of like the circulatory system, responsible for reliably and, importantly, securely transmitting the data collected by the perception layer up to the processing systems. And those could be nearby, maybe at the edge, or far away in the cloud.
So what are the key components here? How does it work?
Well, it involves several critical components. First, you often have gateways. These are really key intermediaries. They gather up data from local sensor networks. See, those sensors might be using short-range, low-power protocols like Bluetooth Low Energy, BLE, or Zigbee, or maybe LoRaWAN.
The ones designed for devices.
Exactly. But those don't usually talk directly to the internet. So the gateway aggregates that data and then translates it into standard internet protocols like TCP/IP, which are needed for longer distance transmission over the bigger network.
Okay, so gateways are like translators and aggregators.
Pretty much.
Yep.
And second, you have the core network infrastructure itself. This could be the public internet, or maybe a company's private local area network, LAN, or wide area network, WAN, or increasingly, cellular networks like 4G and especially 5G, for higher bandwidth stuff.
So choosing the right network seems like a pretty critical decision then. What drives those choices?
Oh, it's absolutely fundamental. It's one of the earliest big design decisions. And it's heavily influenced by things like, well, how much data do you need to send? That's bandwidth. How far does it need to go? Range. How much power can the device use, especially if it's battery powered, power consumption. And of course, the bottom line cost.
You have to balance all those.
You do. For example, something like high definition video surveillance, that needs huge bandwidth, so maybe 5G is the answer there. But for simple environmental sensors sending tiny bits of data just a few times a day over long distances, something like LoRaWAN might be perfect because its power draw is minuscule.
Right.
But the fundamental task, the core job of this network layer, is just ensuring that all that collected data gets routed efficiently and securely to where it needs to go for processing and analysis.
Okay. And once that data has made its journey through the network, what's the ultimate goal? You said it's about delivering value, and that sounds like the top layer, the application layer, right?
Precisely. The application layer, sometimes called the delivery layer, sits right at the top of this three-layer model. And it's the part that the end user, a person or maybe another system, directly interacts with to actually get some benefit.
This is where the magic happens, so to speak.
Kind of, yeah. This is where the data transmitted by the network layer is finally transformed into meaningful information, actionable insights. It fulfills the specific purpose the whole IoT system was designed for in the first place. It covers all the software, the user interfaces, think of mobile apps, web dashboards, maybe integration into bigger enterprise systems
Okay.
that allow users to view the data, maybe control the actuators remotely, receive alerts, and ultimately make informed decisions based on what the system is telling them.
Can you give us some concrete examples? How does this layer actually deliver value in practice?
Sure. Let's think about smart agriculture again. The application layer would be the dashboard that a farmer looks at on their tablet or computer.
Okay.
It shows them, maybe, real-time soil moisture levels from sensors out in the field. It can send automated alerts to their phone saying, hey, Sector 7 needs watering. and maybe even lets them remotely turn on the sprinkler systems for that sector right from the app.
Wow. Okay. That's direct value.
Definitely. Or think about connected healthcare. The application layer could be a secure portal where a doctor can remotely monitor a patient's vital signs, heart rate, oxygen levels, maybe glucose gathered from wearable sensors. They could track if the patient is taking their medication and, crucially, receive immediate alerts if any vital sign goes into a critical range, allowing for faster intervention. In both cases, this layer is where that raw sensor data finally translates into practical, sometimes even life-saving utility.
That's a really clear overview of the basic three-layer model. It sounds pretty intuitive, actually. But you mentioned earlier in the source material notes that it can be an oversimplification. Where does the real intelligence or the heavy processing happen? And what were the specific shortcomings that led to needing a more detailed five-layer model?
That's an excellent question, and it really highlights how IoT has evolved. The three-layer model is fantastic for getting the basic concept across. But as IoT systems grew much more complex, especially when they started being integrated deeply into large enterprise operations.
Right, like in factories or supply chains.
Yeah, exactly. It became pretty clear that the three-layer model didn't fully account for all the sophisticated data processing, the complex analysis, and the business integration steps that were needed.
Yeah.
It kind of lumped too much into the application layer.
Oh, and they needed more granularity.
Precisely. So the five-layer architecture was developed to provide that. It essentially expanded the original model by inserting two crucial intermediate layers between the network and application layers. These are the middleware layer and the business layer.
Okay, middleware and business.
Yeah, and adding these gives you a far more realistic and comprehensive view, particularly for the kind of modern enterprise-grade IoT deployments we see now, which have to handle absolutely massive data volumes and require deep, seamless integration with existing business processes and systems.
Right. This is where it gets really interesting for anyone actually building or managing these large-scale systems. So let's unpack those. Question 4. What are the functions of these two new layers, the middleware and business layers?
Okay, let's start with the middleware layer. You can think of this as the processing layer, or maybe even the brains of the data handling operation.
The brains. Okay.
It sits strategically right between the network layer below and the application layer above. Its primary role is to manage the immense flow of data coming up from the network and also manage the devices themselves. Crucially, a big part of its job is to abstract away the heterogeneity, the sheer variety of all those different devices down in the perception layer.
Abstracting heterogeneity. What does that mean in practice?
It means hiding the complexity. You might have sensors from 10 different vendors, all speaking slightly different protocols or data formats. The middleware layer's job is to smooth that out, to present a standardized, cohesive set of data and services up to the application layer so the app developers don't have to worry about the specifics of each individual device type. This abstraction is absolutely key to enabling IoT to scale effectively. You can't build custom code for every single sensor type when you have millions.
That makes sense. It decouples the applications from the specific hardware. What other specific functions does it perform?
It handles several really vital functions. First, device management. This is huge. It involves provisioning new devices onto the network securely, constantly monitoring the health and status of all connected devices, and very importantly, securely updating the software and firmware on potentially thousands or even millions of devices deployed out in the field, often remotely via over-the-air OTA updates.
Managing the fleet.
Exactly. Second, data processing and abstraction. This is where a lot of the initial number crunching happens. Filtering out noisy or irrelevant data points, maybe aggregating data like taking minute-by-minute readings and creating an hourly average to reduce the volume before sending it further up. It also involves converting data into standard formats and maybe performing some initial time series analysis right after the data comes in.
So prepping the data.
Right. Third, database management. This layer is typically responsible for efficiently storing the vast quantities of data streaming in from the sensor network. And here's a key point. Traditional relational databases often can't keep up.
Why not?
Because the sheer volume and velocity, the speed of sensor data, sometimes thousands of readings per second from thousands of devices, just overwhelms them. So IoT systems heavily rely on highly scalable solutions like NoSQL databases or, very commonly, specialized time series databases.
Time series databases.
Yeah, these are databases specifically optimized to store, query, and analyze data points that are indexed by time. Think sensor readings over time. They make it super efficient to track trends, spot anomalies, and run queries over time windows without the performance bottlenecks you'd hit with a regular database.
Got it. Optimized for timestamped data.
Exactly. And finally, the middleware layer often includes rule engines. These are systems that can execute simple, predefined logic. For example, if the temperature sensor reading goes above 70 degrees Celsius, then trigger an alert. This allows for some immediate actions or notifications without needing the full application layer to intervene for simple rules.
So it handles a lot of the operational intelligence. Where does this layer usually run?
Very commonly, the middleware layer is implemented in the cloud, using platforms like AWS IoT Core, Azure IoT Hub, or Google Cloud IoT Platform. These platforms provide managed services for many of these functions: device management, data ingestion, rules engines, etc. It acts as the engine room, really, preparing that raw data for intelligent use by the applications above it. It's the bridge between just raw bits and bytes and something actually useful.
Okay, so the middleware layer is the heavy lifter, making sense of the data torrent and handling the mechanics. What about the layer above that, the business layer? How does it leverage all this processed information?
Right, the business layer. This is the highest layer in the 5-layer model, and it represents the overall strategic value and the top-level management of the entire IoT system. It's really concerned with the big picture. It leverages the cleaned-up, processed data and the services provided by all the layers below it to achieve core business objectives.
So this is where it connects to the company's goals.
Precisely. Its responsibilities are quite broad and absolutely critical. It includes things like system management, which is about overseeing the entire IoT system's health and performance, managing user accounts and access permissions, maybe handling billing if it's a commercial service.
Okay, overall control.
Yes. And then, crucially, it houses the business intelligence and analytics functions. This is where you apply more advanced analytical tools, often powered by machine learning and AI, to derive high-level insights from that processed IoT data. You're not just looking at one sensor, you're looking at trends across the entire fleet, predicting equipment failures before they happen, identifying optimization opportunities, measuring the actual return on investment, ROI, of the IoT deployment, and ultimately helping business leaders make better strategic decisions based on hard data, not just intuition.
So moving beyond just alerts to actual strategic foresight.
Exactly. That's the goal. It also handles workflow integration. This is super important for enterprises. It's about connecting the IoT system and its data streams with other critical business systems. For example, feeding predictive maintenance alerts into the company's enterprise resource planning, ERP system, to automatically schedule repairs and order parts. Or maybe linking customer device data into the customer relationship management CRM system to provide better customer support.
Making IoT part of the existing business processes.
Yes, not just a standalone thing. And finally, a very important function: privacy and governance. This layer is where the policies are defined and enforced regarding how the IoT data can be used, who can access it, ensuring compliance with regulations like GDPR or IPAW, and managing overall data privacy for users. So you can really see in the 5-layer model how raw sensor readings are progressively transformed first into structured data in the middleware, then into actionable information in the application layer, and finally into tangible business value and strategic insights right at the top in the business layer.
That provides a much richer, more complete picture, especially for complex industrial or enterprise applications. It's a really comprehensive framework. Now let's shift gears a bit from these theoretical models to how things work in practice. When an organization actually decides to build an IoT system, question 5 asks, what's the top-down approach to designing it?
Okay, the top-down approach. This is fundamentally application-driven, or maybe business-driven. It means you start with the end result in mind. The design process begins right up at the highest layers we just discussed, the business and application layers, and then it works its way systematically down towards the physical hardware, the perception layer.
Starting with the why.
Exactly. The very first step, the absolute starting point, is to clearly define the business problem you're trying to solve, or the specific value you want to create. You need a solid business case. For example, the goal might be explicitly stated as, we need to reduce factory downtime by 20% within the next year by implementing predictive maintenance on our critical machinery. Or maybe we want to create a new recurring revenue stream by offering remote patient monitoring services to cardiology clinics. It has to be a concrete objective.
Right, so it starts with that clear problem statement or a specific business opportunity. What happens next?
Once that why is crystal clear, you move down to specify the application requirements. What specific services, features, and user experiences must the application provide to actually achieve that business goal? So, for the factory example, that might mean designing a real-time machine health dashboard for the factory managers, showing key parameters and predictions. For the healthcare one, it might be an automated alert system that notifies doctors instantly if a patient's monitored vitals deviate significantly from their baseline.
Defining the what of the solution.
Precisely. Then, based on those application requirements, you determine the data needs. What specific pieces of information, what data points do you absolutely need to collect from the physical world to power those application features? For the factory machines, you might determine you need high-frequency vibration data, surface temperature, and maybe power consumption readings from each critical motor. For the patient monitoring, it would be things like continuous heart rate, blood pressure readings every 15 minutes, and maybe daily glucose levels.
Figuring out the necessary ingredients.
Exactly. And only then, once you know exactly what data you need, do you finally select the hardware. What specific sensors are capable of accurately collecting that data under the required conditions? What actuators might be needed? What kind of gateways will provide the necessary connectivity? This top-down approach has a huge advantage. It ensures the entire system, from the hardware choices all the way up, is tightly focused on solving a real-world problem and delivering a measurable, clear return on investment. It really helps prevent the common trap of, developing cool technology just for technology's sake, without a clear purpose.
That makes perfect sense. Start with the desired outcome and work backward methodically. Okay, so question 6. What about the opposite method, the bottom-up approach? How does that differ?
Right, the bottom-up approach. As the name suggests, it's the reverse. It's fundamentally technology-driven. It originates down at the perception layer, the hardware, the sensors, the communication tech, and it moves upward, trying to find applications for that technology.
So it starts with a cool new gadget or sensor.
Often, yes. This method is frequently spurred by the emergence of, say, a brand new type of sensor with unique capabilities, or maybe a breakthrough in a low-power communication protocol, or some novel hardware component becomes available and affordable. So the first step here is actually to identify the technology. What are the unique capabilities of this new thing? For instance, maybe a research lab says, we've just developed a new, incredibly low-cost biosensor that could detect this specific protein marker associated with an early-stage disease, and it does it with unprecedented accuracy.
Okay, so you have this new capability in hand.
Exactly. Then the next step is to explore the data potential. What kind of data can this cutting-edge technology actually generate? What are its inherent properties? How often can it take readings? How much data does it produce? How accurate is it really in different conditions?
Understanding what it gives you.
Right. Then comes a brainstorming phase. Brainstorm applications. Given this unique data stream, what potential services or solutions could we possibly build? Using our biosensor example, this might lead to ideas like, wow, maybe we could create an early disease detection screening tool, or perhaps a highly personalized fitness tracking device that monitors recovery markers, or maybe even use it for detecting environmental contaminants in water supplies.
Searching for a use case.
Yes. And only then, after you've brainstormed these potential applications, do you try to develop a business case. Is there actually a viable market for any of these ideas? Is there a sustainable business model? Can we make money or solve a real problem that people are willing to pay for?
So it feels a bit more speculative.
It can be. Now, don't get me wrong. This bottom-up approach is excellent for fostering innovation and potentially discovering entirely new, unexpected use cases that nobody thought of before. But it does carry a significant risk, the risk of developing what people sometimes call a solution in search of a problem. You might build something technically brilliant, but if there isn't a clear, profitable business case or a real user need for it, it might just end up being a cool demo that never takes off.
Right, the classic tech push versus market pull dilemma. So question 7 follows naturally. We have the application-driven top-down and the technology-driven bottom-up. Which approach do you actually see being more successful or more commonly used in practice when people build real IoT systems?
That's a great question. In reality, what you find is that most successful real-world IoT projects don't rigidly stick to just one or the other. They almost always end up employing a hybrid approach.
A mix of both.
Exactly. It combines the strengths of both methodologies. The process often involves a kind of simultaneous and iterative exploration. On one hand, you're deeply investigating genuine business needs and market demands. That's the top-down perspective, keeping things grounded in reality. But at the same time, you're actively exploring the exciting capabilities and possibilities offered by emerging technological advancements. That's the bottom-up, innovation-driven perspective.
It's just more like a loop.
It really is. It becomes an iterative, adaptive process.
Yeah.
You might start with a business need, top-down, explore some tech options, bottom-up, build a quick prototype, get feedback, refine the business case, maybe discover a new technological possibility that changes the application requirements. It's a continuous feedback loop. This hybrid approach allows for a pragmatic design that is both firmly grounded in solving a real-world business problem and agile enough to leverage the very latest technological breakthroughs as they happen. It's about finding that sweet spot between market need and technological capability.
That sounds like a much more realistic picture of how innovation probably happens. Okay, so whether you start top-down, bottom-up, or hybrid, eventually you have to actually build the thing. And as you've hinted, bringing a robust IoT product to market is clearly a far more complex journey than, say, just building a typical mobile app. So, question 8. Can you outline the main stages of the IoT development lifecycle for us? What does that whole journey look like?
You're absolutely right. It's a multi-stage process, and it extends far beyond just writing some code or designing a circuit board. The IoT development lifecycle really encompasses the entire journey, right from the very first glimmer of an idea all the way through to continuous ongoing operations, possibly for years.
Okay, so where does it start?
It all kicks off with ideation and requirement analysis. This is the crucial what and why phase. It's not just a quick brainstorm. It involves potentially extensive market research to see what's out there, identify gaps or opportunities. It means doing thorough stakeholder interviews, talking to potential users, business managers, maybe even field technicians to capture all their needs and pain points.
Getting all the requirements down.
Exactly. And the output isn't just a vague idea. It should be a detailed requirements document. This specifies the system's high-level goals, the desired features, critical operational constraints, things like target cost, maximum power consumption, maybe the environmental conditions it needs to survive, and, very importantly, clear metrics for what success will look like. How will we know if this thing is actually working and delivering value?
So, a solid foundation. What's next?
Next comes system design and architecture. Based on those meticulously gathered requirements, the high-level architecture of the entire system is designed. This is where those really crucial foundational decisions are made. Are we going with a 3-layer or a 5-layer model view? Which specific microcontrollers, MCUs, have the right balance of power, performance, and cost? Which sensors meet the accuracy requirements? Which communication protocols, Wi-Fi, Bluetooth, LE, LoRaWAN, cellular, make the most sense given the range, bandwidth, and power constraints? And which cloud platform like AWS IoT, Azure IoT Hub, Google Cloud IoT offers the services and scalability we need?
These sound like decisions with big consequences down the line.
Huge consequences. They will profoundly impact the system's performance, its final cost, its security posture, and its long-term viability and ability to scale. You have to get this stage right.
Okay, architecture is set, then you build.
Then you move into prototyping and development. This is where the design starts to become tangible. It typically begins with building a proof of concept, or POC. Often, this uses off-the-shelf development boards, things like Arduino or Raspberry Pi are popular for this, along with readily available sensors. The goal isn't to build the final product, but to quickly validate the core idea, test the riskiest technical assumptions, and show that the basic concept is feasible before you invest heavily in custom development.
De-risking the project early.
Exactly. Once that POC is validated and everyone agrees the core idea works, then full-scale development proceeds. Often in parallel tracks, which I know is our next question.
Right, but before we get to parallel tracks, what comes after development?
After development comes testing and quality assurance, QA. And this is absolutely critical and often more complex for IoT than other software, because you're dealing with this intricate mix of hardware, low-level firmware, network communications, cloud back-end software, and front-end applications. You need rigorous, multifaceted testing to ensure the whole system is reliable, performs under load, and is secure. We'll touch on the specifics of testing later, too.
Okay, test, then launch.
Then, assuming it passes testing, you move to deployment and launch. The system is actually rolled out into its production environment. This might be done in phases, maybe a small pilot deployment with a few friendly users or locations first, before a wider, full-scale launch. This phase includes potentially complex logistics like the physical manufacturing of the hardware devices if you've designed custom hardware, securely provisioning each device, which means registering it and configuring it for the network, and deploying all the cloud-based software infrastructure.
Getting it out into the real world.
Right. But the journey doesn't end there.
Yeah.
This is a key difference with IoT. There's the final, ongoing stage, maintenance and operations. IoT systems aren't usually fire and forget. They require continuous monitoring and maintenance throughout their entire operational lifespan.
What does that involve?
It involves actively managing that fleet of devices out in the field, tracking their health, diagnosing issues remotely. It means having a mechanism for pushing those over-the-air OTA firmware updates to fix bugs discovered after launch, patch security vulnerabilities, or even add new features. It requires diligently monitoring the cloud infrastructure for performance, availability, and security threats. And it means providing ongoing customer support. This ongoing operational phase is a critical and honestly often underestimated component of the total lifecycle cost and complexity of running an IoT solution. It's not a one-time effort.
That's a truly massive undertaking, clearly requiring tight coordination across many different disciplines: hardware, software, networking, operations. You mentioned that once a proof of concept is validated, development often proceeds in parallel tracks. Question 9 asks, what exactly are those different tracks of work that need to happen simultaneously to build the full product?
Right, so that PC, using maybe off-the-shelf parts, prove the core concept works. Now, to build the actual, scalable, potentially custom product, the development effort typically branches out into 3 distinct, yet highly interconnected parallel work streams. They have to happen at the same time because they depend on each other.
Okay, what's the first track?
The first is hardware firmware development. This is where the team focuses on designing the custom printed circuit boards, PCBs, if needed. These boards will house the chosen microcontroller, the sensors, the communication modules like Wi-Fi or LoRa chips, power management circuits, everything. And critically, this track also involves writing the low-level firmware. This is the software that runs directly on the embedded microcontroller inside the device.
The device's own brain.
Exactly. This firmware is responsible for controlling the sensors, reading data from them, managing the device's power consumption, which is super critical, as we'll discuss, handling basic error conditions, and managing the device's fundamental connection to the network layer. It's very specialized, close to the metal programming.
Okay, hardware and the software living on it. What's the second track?
The second track is cloud backend development. This is where all the heavy lifting we talked about for the middleware layer and potentially parts of the business and application layers actually gets built. It involves architecting and coding the scalable infrastructure, setting up the databases, like those time series databases, building the application programming interfaces, APIs, that the devices and the front-end apps will use to communicate. This all happens on the chosen cloud platform, AWS, Azure, Google Cloud, or maybe even a private cloud.
So building the server-side intelligence and data handling.
Precisely. This backend is absolutely crucial for ingesting potentially massive streams of data from thousands or millions of devices, processing it, storing it securely and efficiently, and then delivering the right information to the right user or application at the right time. This is also where you implement more complex logic, analytics, and decide on data processing patterns like, do we need real-time stream processing for immediate alerts, or is nightly batch processing okay for generating reports?
Makes sense. And the third track?
And the third track, running in parallel, is application development. This focuses on creating the front-end user interfaces, the parts that humans actually interact with. This could be designing and building native mobile applications for iOS and Android smartphones, developing web-based dashboards for monitoring and control accessible via a browser, or maybe building integrations that plug IoT data directly into existing enterprise software that people already use.
The user-facing part.
Exactly. These applications are responsible for visualizing the data in a meaningful way, allowing users to perhaps send commands back down to the actuators on the devices, managing user accounts, and providing the overall user experience, UX, for the IoT system.
And you said these run in parallel.
Yes, and that's key. They have to progress simultaneously, and there needs to be constant communication and integration points between these 3 teams. Why? Because a decision made in hardware design, like changing a sensor, might impact the firmware. A change in the firmware, like the data format, will impact the cloud backend. And change in the backend API will definitely impact the front-end application. They are deeply interconnected. So agile methodologies and strong communication are essential to keep everything aligned.
It really underscores the complexity. Given all those parallel tracks and the sheer number of interacting components, hardware, firmware, multiple network layers, cloud services, applications testing, and IoT system, as you mentioned, sounds particularly challenging. So question 10. What are some of the different facets of testing required to ensure everything actually works reliably and securely together?
You're right, it is incredibly complex, and that demands a testing strategy that's equally comprehensive and multifaceted. You simply can't just test one piece in isolation and hope for the best. The interconnectedness means you need a holistic approach covering many different angles.
Okay, so what's the first angle?
Well, first, there's hardware testing. This goes way beyond just checking if the device powers on. It involves ensuring the physical device is robust, reliable, and durable, especially considering the environment where it might be deployed. Think about stress testing under extreme temperatures, high humidity, vibration, maybe even water ingress testing or shock resistance testing, depending on the use case. It also includes component-level testing, detailed power consumption profiling under different operating modes, and ensuring electromagnetic compatibility, EMC.
Making sure the physical thing holds up.
Exactly. Then perhaps, obviously, connectivity testing is vital. You need to rigorously verify that the device can reliably connect to the network and transmit its data under a whole variety of, and often challenging, network conditions. This isn't just testing in a perfect lab environment. It means testing with intermittent or spotty connectivity, varying signal strengths like moving from strong Wi-Fi to weak cellular, high network latency, packet loss, and testing how the device behaves when switching between different communication protocols or network types, if applicable. Does it recover gracefully? Does it buffer data correctly?
Testing the internet part of IoT.
Precisely. Next, and this is huge, security testing. We already flagged security as a major challenge, so testing for it is paramount. With IoT's massive attack surface, this requires dedicated effort. It includes things like penetration testing, actively trying to hack the system, and vulnerability analysis across all layers. Can you physically tamper with the device to extract keys? Can you eavesdrop on the network traffic? Is the firmware secure against reverse engineering? Are the communication protocols encrypted properly? Can you find flaws in the gateway software? Are the cloud APIs secure against unauthorized access? You have to look everywhere.
A daunting task. What else?
Then there's performance and scalability testing. This is crucial for ensuring the back-end systems can actually handle the load when the system scales up. You can't just test with 10 devices. You need to simulate thousands or even millions of devices connecting simultaneously, sending data streams, maybe requesting updates. This involves load testing to find the breaking point, stress testing to see how it behaves under extreme load, and identifying potential bottlenecks in the data ingestion pipeline, the processing engines, or the database. Can the system handle the expected peak load, and can it scale gracefully as more devices are added?
Planning for success, essentially.
Yes, you have to. And finally, don't forget usability testing. This focuses on the end-user experience, usually with the application layer interfaces. Is the mobile app intuitive? Is the data dashboard easy to understand and navigate? Can users easily find the controls they need? Does it actually help them achieve their goals effectively? Even the most technically brilliant IoT system can fail if the end users find it confusing or frustrating to use. So, getting real user feedback here is critical. Each of these testing facets is non-negotiable for launching a successful, reliable, and resilient IoT deployment.
Wow, that is an exhaustive list of testing dimensions. It really paints a picture of the engineering rigor required. So, given all those inherent complexities we've discussed in design, development, and testing, let's move to question 11. What is considered to be the single greatest overarching challenge in IoT design and implementation today?
Yeah, if you had to pick just one, the consensus across the industry, and definitely highlighted in the source material, is security. It remains, without a doubt, the single greatest and most persistent challenge in the entire IoT domain.
Why is it so much harder in IoT?
It boils down to the sheer scale and the nature of the systems. You have this vast, distributed attack surface. Think about it. Every single sensor out in the field, every actuator, every gateway device sitting in a factory or home, every communication channel it uses, every API endpoint in the cloud. Each one represents a potential point of entry for an attacker, a potential vulnerability.
An attack surface orders of magnitude larger than traditional IT.
Exactly. And the threats exist at absolutely every layer of the architecture we've discussed. Down at the perception layer, you worry about physical tampering, someone accessing the device to steal cryptographic keys or install malicious firmware. At the network layer, you worry about eavesdropping on data transmissions if they're not encrypted, denial of service attacks flooding the network, or malware infecting gateways to use them as beachheads. Then, up in the middleware and application layers, you face significant risks of cloud data breaches, unauthorized access to sensitive data stores, compromised user applications, or even attackers sending malicious commands down to actuators.
It's a minefield.
It really is. And that's why a security by design approach isn't just, a nice-to-have best practice. It's absolutely essential for survival in IoT. It means you have to think about and integrate robust security measures right from the very beginning throughout the entire development lifecycle we just outlined.
Not just bolting it on at the end.
Never. It has to be baked in. That means things like ensuring secure boot processes on the hardware itself so it only runs trusted firmware, using tamper-resistant hardware where possible, implementing strong end-to-end encryption for all communications, managing device identities and credentials securely, using robust authentication and authorization for cloud access, patching vulnerabilities quickly via secure OTA updates, and continuously monitoring for threats. Ignoring security or treating it as an afterthought is simply not an option. It's the absolute foundation of building trust in any connected system, especially ones controlling physical processes or handling sensitive data.
That's a huge ongoing hurdle to overcome, especially with the sheer number and often low-cost, though power nature of many IoT devices, making robust security harder to implement. Okay, so security is number one. Question 12 asks, besides security, what is another really significant barrier to creating truly integrated, seamless, and widely adopted IoT systems?
Another major barrier, and it's somewhat related to the complexity highlighted by security, is the challenge of interoperability and standardization.
Meaning things don't talk to each other?
Pretty much, yeah.
Yeah.
The current IoT landscape is, unfortunately, still quite fragmented. You have a vast array of proprietary technologies, different communication protocols, different data formats, and competing standards, often pushed by different vendors who want to lock customers into their specific ecosystem.
Creating walled gardens.
Exactly. That's the term often used. It means that devices from manufacturer A often simply cannot communicate or share data effectively with devices or platforms from manufacturer B, or sometimes even between different product lines from the same manufacturer, if they haven't prioritized interoperability.
What problems does that cause?
Well, this fragmentation creates several big problems. It leads to vendor lock-in, making it hard for customers to switch or mix and match best-of-breed solutions. It significantly increases complexity for developers who have to deal with multiple different APIs and protocols. And fundamentally, it severely hinders the development of truly integrated, seamless IoT systems where data can flow easily between different devices and services to create more powerful, holistic solutions. Imagine a smart home where your security system can't talk to your lighting system, or a smart city where the traffic management system can't get data from the public transport system.
It limits the potential value.
Massively. Now, there are efforts underway. Organizations like the Open Connectivity Foundation, OCF, the Connectivity Standards Alliance, Matter, the Thread Group, and various industry-specific consortia are actively working hard on establishing common protocols, data models, and frameworks to try and bridge these gaps. But achieving truly universal, seamless interoperability across the incredibly diverse world of IoT devices remains a considerable ongoing challenge. It's a significant barrier to broader adoption and realizing the full, synergistic potential of interconnected systems.
That's certainly a real pain point you hear about a lot, slowing down market adoption and innovation. Okay, shifting focus slightly. Question 13. For many specific types of IoT devices, particularly those that are battery-powered and deployed in remote, maybe hard-to-reach locations, like those environmental sensors you mentioned in a vast agricultural field, or perhaps critical monitoring equipment on remote industrial pipelines. What is a really critical design constraint that engineers and designers are constantly wrestling with?
Ah, yes. For those specific but very common use cases, battery-powered devices in remote spots, power management becomes an absolutely critical, sometimes the most critical, design constraint. It often takes precedence over almost everything else, even cost sometimes.
Why is it so paramount there?
Think about the logistics. Imagine you've deployed thousands, maybe tens of thousands, of sensors across a vast, inaccessible mountain range to monitor wildfire risk, or maybe across hundreds of miles of remote pipeline. A device that needs its battery changed every few weeks or even every few months is simply impractical. The cost and effort of sending technicians out to replace batteries across such a large fleet would be astronomical and would completely negate the business case for the deployment.
That has to last for years.
Years, ideally, sometimes 5, 10 years, or even more on a single battery. This necessitates deep, specialized expertise in several areas. First, low-power hardware design, choosing components like ultra-low-power microcontrollers and sensors that sip tiny amounts of current, especially when they're in sleep mode. Second, writing extremely energy-efficient firmware. The code has to be optimized to keep the device in its deepest possible sleep state for as long as possible, only waking up briefly to take a reading and transmit data, minimizing the processing cycles and the time the radio is active.
Every microamp counts.
Absolutely. And third, critically, it involves the strategic use of those low-power wide-area networks, or LP1s, that we touched on briefly earlier. Technologies like LoRaWAN or NB-IoT, narrowband IoT, are specifically designed for exactly this scenario. They offer long-range communication kilometers, potentially, but use incredibly small amounts of power for transmission compared to, say, Wi-Fi or even traditional cellular. Choosing the right LP1 technology and optimizing its use is fundamental for achieving that multi-year battery life. So it's not just about the battery itself, it's this holistic combination of hardware, firmware, and network choice that makes long-term remote deployment feasible. It dictates the total cost of ownership and whether the solution is viable at all in those challenging environments.
That interplay between hardware, software, and network for power is fascinating. And just to be comprehensive, as we're discussing these significant challenges, the source material also highlights two others that are almost equally fundamental: scalability and data management and analytics. Can you briefly elaborate on those as well? They seem tightly linked to everything we've discussed.
Absolutely, they're huge and deeply interconnected challenges in their own right, underpinning much of what makes IoT hard. Let's take scalability first. This is all about the ability of an IoT system to, well, scale, to gracefully handle potentially exponential growth in the number of connected devices and the sheer volume of data they generate. Designing a system that works beautifully with 10 devices in the lab is one thing. Designing an architecture that can smoothly transition from that prototype stage to a whole deployment supporting 10 million devices without falling over or becoming prohibitively expensive is an entirely different and much harder challenge.
Designing for massive growth from day one.
You have to. The architecture must be designed with scalability in mind right from the start. This means making careful choices about using inherently scalable cloud services like serverless computing, auto-scaling databases, selecting efficient and lightweight communication protocols that don't overload the network, and designing data processing pipelines that can handle massive, concurrent data streams without creating bottlenecks or failing under pressure. It's really about building for the future growth you anticipate, not just the immediate needs of the pilot.
Okay, and the other one, data management and analytics.
Right. This ties back to the middleware and business layers. The sheer volume, terabytes, petabytes of data, velocity, data streaming in constantly, sometimes milliseconds apart, and variety, data from different sensors in different formats, structured and unstructured, generated by large-scale IoT systems, presents a classic big data challenge, but often with even more real-time constraints.
The 3 V's of big data amplified.
Exactly. Just storing, processing, and analyzing the tsunami of data to extract timely and meaningful insights is an incredibly complex task. It requires sophisticated data pipelines to ingest, clean, transform, and route the data correctly. It needs those highly scalable databases we talked about, like time series or NoSQL databases, that can handle the load. And crucially, extracting real value often requires advanced analytics, frequently incorporating machine learning, ML, and artificial intelligence AI models.
Why ML and AI?
Because the patterns you're looking for, predicting machine failure from subtle vibration changes, optimizing energy consumption across a city grid based on real-time demand and sensor readings, identifying anomalies in patient data that indicate a problem, are often too complex or hidden within the noise for simple rule engines or traditional statistical analysis to find. ML models can learn these patterns from historical data and make predictions or identify outliers much more effectively. It's about moving beyond just monitoring what happened towards predicting what will happen, predictive analytics, and even recommending what should be done about it, prescriptive analytics. It's how you transform all that noisy sensor data into genuine foresight and actionable intelligence.
So we've thoroughly mapped out the architectural models, we've explored the different design approaches, dissected the complex development journey, and really grappled with the formidable challenges: security, interoperability, power, scalability, data. To bring all of this together now for our final question, number 14. What is the single key takeaway message regarding the fundamental importance of architecture in any successful IoT system?
I think the key takeaway, the core message that runs through everything we've discussed, is but profound and fundamentally practical. A well-defined, robust architecture is the invisible yet absolutely indispensable backbone of any successful Internet of Things system.
Invisible but indispensable.
Exactly. We've seen how both the foundational 3-layer model and the more comprehensive 5-layer model provide those essential blueprints. They're not just academic exercises, they're practical frameworks for organizing the incredibly complex flow of information, for systematically transforming that raw physical data from sensors into tangible business value or user benefit at the application layer.
It provides the structure for value creation.
It does. And understanding the different strategic design approaches, whether you start top-down driven by the application or bottom-up driven by technology, or, more likely, use that pragmatic hybrid model, and then diligently navigating that rigorous multi-stage development lifecycle we outlined. These are absolutely fundamental steps to translate an innovative IoT idea into a reliable, secure, scalable, real-world solution. The architectural plan you lay down doesn't just dictate how the system functions on day one.
Right.
It fundamentally predetermines its capacity for future growth, its resilience against the inevitable cyber threats, its ability to interoperate and integrate with other systems, and ultimately its long-term viability and its actual ability to deliver on the original promise. Getting the architecture right is often the crucial difference between creating a fleeting gadget that fails to scale or secure itself and building an enduring, transformative, industrial-grade solution that delivers real value for years to come.
And if we really connect this to the bigger picture, all that transformative power we hear about with IoT, the potential to optimize entire factories, create truly smart and efficient cities, enable highly personalized remote healthcare, revolutionize agriculture, and so much more, all of that potential is entirely enabled, but also constrained by this underlying architectural structure.
That's perfectly put.
It's what elevates a concept from just being a collection of cool, connected gadgets into something genuinely robust, reliable, and industrial grade. However, as we've spent a good amount of time discussing, the path to realizing that potential is indeed laden with very significant challenges. Overcoming those hurdles of security, achieving interoperability, managing scalability, optimizing power consumption, and taming the complexities of massive data management isn't merely a technical exercise for the engineers.
No, it's more than that.
It feels like a fundamental prerequisite for building trust with users and businesses, for ensuring the resilience of these increasingly critical systems, and for truly unlocking the full world-changing potential that this technology holds.
Couldn't agree more. As we look forward, as IoT becomes even more pervasive and integrated into the fabric of our lives and industries, the principles of sound architecture and deliberate, well-considered design will only grow in importance. They serve as the essential guideposts for constructing the safe, efficient, secure, and truly intelligent connected world of tomorrow. The architectural decisions being made right now, today, will absolutely define the capabilities, the limitations, and the trustworthiness of our future digital infrastructure.
What a comprehensive deep dive. This has been incredibly insightful. We've covered so much ground from those foundational 3-layer and 5-layer blueprints of IoT architecture through the strategic top-down, bottom-up, and hybrid design approaches, the complex multi-stage development lifecycle, and a very candid look at the critical challenges like security, interoperability, power, scalability, and data management that absolutely must be addressed for any successful implementation.
Yeah, it really highlights that understanding these architectural models, thinking strategically about design, navigating that full life cycle, and proactively tackling those significant challenges, they aren't optional extras. They're all pretty much non-negotiable for building IoT systems that are robust, reliable, secure, and actually future-proof.
It's clearer than ever that without that solid architectural plan, even the most innovative IoT ideas can easily crumble under their own weight, or at best, fail to scale or deliver sustainable value.
Absolutely. Architecture first.
Indeed. And if you found this deep dive into the structure and design of IoT fascinating, then you definitely won't want to miss our upcoming installment in this series. Please tune in for our next deep dive, where we'll be focusing on hardware and Internet of Things, sensors, actuators, and microcontrollers. We'll be getting even closer to the physical things that start this whole process.
Yeah, that promises to be just as insightful. We'll really dig into the tangible components operating right at the very edge of the IoT ecosystem. The actual sensors gathering the data, the actuators making things happen, and the tiny microcontrollers that orchestrate it all.
Looking forward to it. Thank you all so much for joining us today for this deep dive into IoT architecture and design principles. For more insights and explorations into the cutting edge of technology, please be sure to subscribe to our channel, Tech AI and Beyond.
Thanks, Edward.
We'll see you next time.